Hi, my name is John Regehr, and today Nuala and I would like to talk to you for a little bit about attributes. So the first thing we'd like to look at is what attributes are used for. So at a high level, what attributes are used for is to communicate language level invariance from compiler front ends to the middle end and back ends of the compiler. And so the idea here is that sometimes the programming language knows things that will be difficult to recover through static analysis, so we can make compilation faster by communicating those directly to the middle end and back end. And other times, the front end knows things that can't be inferred even in principle by a middle end or back end, and so these need to be supplied, and so that's what the attributes do. Another thing attributes use for is to provide a first-class representation for static analysis results. And this first-classness is nice because what it means is we can include these attributes that indicate the results of analyses in test cases, and we don't need to then run the static analysis every time we run the test case. And then also, these can serve as a cache. So the analyses might be expensive, and then so these attributes can then be used to preserve the analysis results for as long as they're valid, and we don't need to keep rerunning the analyses. So that's what attributes are for. And next, let's look at what they can do for us. So one thing attributes can do is remove behaviors from code. So for example, the write-only attribute, when applied to a function, implies that that function doesn't read any memory. And so removing behaviors in this fashion is useful because this supports optimizations. On the other hand, removing the behaviors for functions is dangerous because transformations on those functions need to be careful to respect the attribute. So recently, for example, we ran into a case where loop invariant code motion can introduce a load into a function that has the write-only attribute set. And so this isn't hard to fix. We could either have loop invariant code motion remove the attribute when it introduces a load, or it could just not do that particular transformation when write-only is there. But either way, that bug is there, and it's gonna sort of need to be fixed. And it's sort of very easy for these things to happen because the people writing optimizations are not necessarily super aware of the full set of attributes, or they're not necessarily thinking about that all the time. Another thing attributes can be used to do is add behaviors to functions. So for example, the convergent attribute says that a function with this attribute is sort of a non-standard function. It has non-standard semantics, and we can't do all of the transformations to that function that we can do to regular LLVM functions. So adding behaviors to functions is even more dangerous than removing them because all the way from day one, as soon as this attribute lands, all optimization passes have to be correct with respect to it. We can't sort of add the attribute and then add things that use it later. We need to sort of get this right in advance. And this kind of attribute can't be safely dropped like the other kind can. And this makes them sort of extraordinarily tricky and dangerous to introduce into our compiler. Okay, so those are the things that we can accomplish using attributes. And so now let's sort of look at the big picture with respect to them. So currently in LLVM, there are 69 attributes that can be applied to functions. And there's overlap between them. So for example, a minute ago we looked at the write-only attribute, but there's also a read-none that is sort of similar. It's different, but it overlaps semantically somewhat. So there's a fair amount of overlap between attributes. There's quite a few of them. And then furthermore, the semantics of these attributes can be sometimes unclear. So the dynamic here is kind of that people want to support some optimization. They want to support some transformation. And to justify that transformation, they add an attribute that communicates the necessary information to make that transformation safe from some other part of the compiler. So that's good and it works. But the problem is people sort of do this separately. They do this one at a time, and they do this without necessarily looking at the big picture of all the attributes that are already there. And what this does is, over a period of a number of years, leads to kind of a murky, non-orthogonal situation. And so the deal is attributes interact with each other. They interact with most of the rest of the compiler. And this is fairly difficult and hard to maintain because we get kind of an n-squared interaction problem. So that's the current situation. And the question is, what do we want to do about it? And so basically, here's what we think. We think that the existing set of attributes needs some cleaning up. We need to carefully define the semantics and even maybe formally define them, as we're often trying to do in Alive 2. We need to look for overlap between different attributes and look for places where the defaults are set incorrectly. So what we'd like is sort of a minimal orthogonal set of attributes, and that's not really exactly what we seem to have right now. So looking forward, we should make the bar for adding a new attribute quite a bit higher. So instead of just asking, does this attribute support some sort of a desirable optimization, we want to rather ask something like, is this attribute part of a coherent bigger picture that we can maintain indefinitely moving forward? And so overall, there's this sort of high-level question, what is the correct set of attributes to support in a compiler like LLVM? And this is a really hard question. It's not at all easy, and it's one that really hasn't gotten enough attention. And so that's kind of the purpose of our talk here, is to bring attention to this problem, to call attention to it, and to try to get some discussion going about this. Thank you.